In the world of remote sensing, two powerful technologies act as the eyes of Earth observation. SAR and LiDAR. Both reveal what the human eye, and even ordinary satellites, cannot see. But they do it in very different ways. Today, let's explore SAR versus LiDAR, how they work, what makes them unique, and when each technology is the better choice. What is SAR? Synthetic Aperture Radar. SAR stands for Synthetic Aperture Radar, a microwave-based remote sensing system. Unlike optical sensors that depend on sunlight, SAR actively emits radar signals toward the Earth and measures the reflections that bounce back to the sensor. Because it uses microwave frequencies, SAR can penetrate clouds, smoke, and even darkness, giving us a consistent, all-weather, day and night observation capability. Imagine trying to observe a flooded region during a storm. Optical satellites would see nothing but clouds. SAR, however, sees right through, providing clear radar images of the affected area. This makes SAR ideal for flood mapping and disaster monitoring, land deformation and subsidence studies, glacier and ice monitoring, soil moisture and surface roughness detection, forest biomass estimation. SAR also has a unique ability called interferometry, or SAR, which can detect ground movement with millimeter-level precision, used in earthquake, volcano, and infrastructure stability studies. How SAR works, simple explanation. A SAR sensor sends out a radar pulse, which hits the ground and bounces back. By measuring how long it takes for the signal to return, and the strength and phase of that return, SAR builds an image of the surface. Because the satellite moves along its orbit, the synthetic aperture technique combines multiple radar returns over time to simulate a very large antenna. This is how SAR achieves high spatial resolution even from hundreds of kilometers away. SAR doesn't capture light intensity, it records backscatter strength, how much radar energy is reflected back. Bright areas represent strong reflections, like buildings or rough terrain, while dark areas show weak reflections, like calm water or smooth surfaces. What is LiDAR? Light detection and ranging. LiDAR, on the other hand, uses laser light instead of microwaves. It emits rapid pulses of laser energy, often hundreds of thousands per second, and measures how long each pulse takes to return after hitting the ground or objects like trees and buildings. Because light travels at a known speed, the LiDAR sensor can calculate precise distances to millions of surface points, generating a detailed 3D point cloud of the terrain. LiDAR works best in clear, daylight conditions, and is commonly used in airborne or drone-based surveys, where high precision and fine spatial detail are needed. What LiDAR reveals? LiDAR provides incredible vertical accuracy, often just a few centimeters, making it perfect for topographic mapping and digital elevation models, DEM/DTM, urban planning and building height analysis, forest canopy and biomass studies, power line and road corridor mapping, coastal and river morphology surveys. One of LiDAR's greatest strengths is that it can see through vegetation gaps, allowing scientists to measure both the canopy height and the ground surface underneath, something optical or radar sensors often struggle with. Real-world applications. Let's compare a few examples. During floods or storms, SAR satellites like Sentinel-1 or RadarSat can capture flooded zones through clouds, LiDAR cannot. For mapping urban structures or forest canopy, airborne LiDAR systems can model every building and tree with centimeter accuracy. SAR would give only rough outlines. In monitoring land deformation, SAR interferometry, in SAR, can detect ground movements smaller than a centimeter. LiDAR would miss such subtle motion but capture detailed shape instead. Both are powerful, they simply see the world in different ways. When SAR and LiDAR work together. In modern Earth observation, SAR and LiDAR are often used together. For example, LiDAR can create accurate elevation models, while SAR provides information about surface moisture or changes over time. Combining both gives scientists a complete view, the structure and the dynamics of our planet. This fusion is used in 1. Disaster response. 2. Environmental monitoring. 3. Deforestation and carbon stock analysis. 4. Infrastructure and urban expansion studies. So, to summarize, SAR uses microwave radar. It sees through clouds, operates day and night, and measures surface roughness, moisture, and deformation. LiDAR uses laser light. It captures fine, 3D details of terrain, vegetation, and buildings under clear skies. Together, SAR and LiDAR form the two complementary eyes of modern Earth observation, one revealing surface texture and motion, the other uncovering structure and form. If this video helped you understand how SAR and LiDAR differ, and why both matter, make sure you like, subscribe, and share it with your fellow geospatial learners. Comment below. Which one do you use more, SAR or LiDAR? Stay tuned for our next tutorial on radar interferometry and LiDAR-based terrain modeling. Thank you for watching.